This is part 2 of lesson 5.6, analyzing logarithmic functions. Just to recap, this lesson, we're looking at determining the value of a log using the change of base formula and sketching the transformation of a graph, transformation graph of a log function. Just remember that to complete these questions, I'll go through these questions today and a review our change of base formulas, log b x equal to log x for log b, which b is 10, and our transformation function is y minus k equals c log a dx minus h, or also written in this form on the right. So we'll go through these questions and maybe one or two more today. So we're referring to these change of base formula and your log transformation. But let's look at the first question, which we're using the change of base. Approximate the value of each log to the nearest thousands. Write related expression in exponential expression. So let's look at the first one. Remember, this is using the change of base formula. So let's remind ourselves what it is. So change of base formula is log. So change of base. So we have log b to the x is equal to log x over log b. Look at a. So we have, and that will give us equivalent of, so log 550 will be equivalent to log 50 over log 5. And this will be need our wonderful calculator here. So log 50, and this now is base 10. So we have log 50 divided by log 5 gives me a result of a 2.4367. So 2.06. Oops. Goes on. So log 550 is equal to this. So we can say the exponential. So 50 can write this. So 50 is equal to 5 to the power 2.4306. So we can say approximately. So that's writing it in an exponential form. So log 86 can be written as log 6 over log 8. So we have, it should be equal to so log 6 divided by log 8 give us a result of 0. So we can say prog 8616. So it goes on. So if you write it, you see log 86 equal to approximately 0.8616. So we can write that exponential 8. Right. So we can say that 8 to the power is equal to 6. So we have 8 to 0.8616. It's approximately 6. So that's an exponential form. So just remember you're applying the change of base formula. So a over b, or x over b. Use your calculator, use base 10. Once you know what your log is, that's your exponential for the base. So the base is 8, exponential is 0.8616 approximately, equivalent to 6. There are a few other examples. Example 3, question 3 in your booklet. The same principle applies here. And in this case, we're using, still applying the change of base formula, which is, let's write it out here, xb is equal to log b over log x. Where does it matter? I think I switched it here, but it could be either way. So let's look at the first one we have here. Let's give me log 2,9, going to give me log 9 over log 2. Use my wonderful calculator again to up with. So log 9 by log 2, 3.1699. So log 2 to 9 is approximately 3.1699. So we can write that to an exponential form. If you want to write exponential, it would be 2 to the 3.16. Approximately, and 99 is equal to approximately 9. So here we have log 2, so we can put that as log 100 divided by log 2, which is 6 point, I use my calculator, so we can conclude log 200 is approximately 6.6438. We can write as exponential base, the exponent, so it'll be 6.6438, approximately 100. The next set of questions, you basically have to find the log for each one, and then you determine which one is from the greatest to the least. So largest to smallest. Let's look at each one. So let's find log 2 to the 80. So log 8 for log 2. And this will give me what? Log 8 over log 2. 3. Oh, is that correct? No, it should be log 80. No, I'm doing log. I'm just following what's here incorrect. Okay, so let's do that again. It's log 80 divided by log 2. 6.3219 approximately. Okay, then we have log 3 900, which is which works out to be 6.1918. My beautiful calculator here. Let's see what would I get here. Log 5,000 divided by log 4. 6.1438. 6.1438. The final one, log 5 to 10,000. $5.7227. So what we find here, the greatest is log 280. Then we go to log 3 900. No, need the order. Okay. So we can see this is 1, that's 2, 3, and 4. Okay, so it's a good practice using the change of base formula. To a couple more, approximate value near stamp exponential form, which is very similar. So we have log 400 over log 7. And this worked out to be, get my calculator ready here. So we have 3.079. So 3.0790. So log for 400 is equal to approximately. So exponential form will be 3.0790, approximately 400. Log of 3, that's interesting one. So this is half, so this could be equal to log a half. So it should be equal to, we can put that out. So log 0.5 divided by log 3 give us negative 6.3102, etc. Log 3 to half is approximately negative So 3, 1. So we can write 3 to the negative 0.631 is approximately a half. So check your work against the solutions given. Now we're going on to a transformation of log. So this is your check your understanding question 3, which is found on page 403 to 404. So it's very similar question to what we've done earlier. In lesson 1, so they asked you to create a table of values for log 2 of x. So the step for the A, what you want to do is to write the log as an exponential. So write for y equal log 2x as exponential, which is 2 to the y. We have 2 to the y. This is my exponent here. Is equal to x. So that's what I did here. So this is my log y is equal to log 2x. So I'll create a table of values for these. And then I'll use my x and y coordinate for my transformation. I'll look at part B in a moment. But let's proceed with part A. So you have 2 to the y is equal to x. Now, as I mentioned in a previous lesson, you select the y because then you can find the x value from the y. So if y is negative 2, x will be 2 to the negative 2. So we put here 2 to the negative 2, which is 1/4, or 0.25. Then this will be 2, because this is our x is equal to 2 to the power y, negative 1, which is a half, then 0, 2 to the power 0, which is 1. So coordinates for that is 1, 0. Then we have 2 to the power 1 is equal to 2. 2 to the power 2 is 4. So now we have our x and y coordinates. Our table of values for y equal to log 2x. Now let's sketch that graph. And I have again here. So I'll just move this up a little bit here so I can get a view. Now, the first point is x is a quarter, y is negative 2. So here we have a quarter, negative 2. Then we have x is a half, y is negative 1. X is 1, y is 0. So that gives us our x-intercept. True to form. And then we have x is 2, y is 1. Finally, x is 4, y is 2. You could go ahead and 3 will give us enough. We probably could get another one here. No graph here. If we have x is y is 3. And what do we get here? If y is 3, x would be what? 2 to the power of 3, which is 9. Oh, yeah, we can put 1 in there. 9, 3 here. So now we have our graph. But this is y, and this is x. So this is my graph. Y is equal to log 2x. Now, let's look at our transformation graph now, function. We're going to sketch this graph. But if you look at this graph here, we're going to compare it with a standard graph. So we'll write it down here. So for this is for B, we have y is equal to 2 log 2, 2x minus 1. By the way, there's no brackets here. So remember, this is your vertical translation. Okay. So if you look at this now, this would be our k. Right, this is our k. K is equal to -1. Now h, there's no h. Remember our standard formula, if you go back, is dh. So we have a k across here. So here we are. So the k, if you look at this here, I'll just put it side by side. So k is -1. There's no h, right? So we put 0 there. The d, you get here. Now, d is always 1 over, so it'd be 1 over d, which is 1 over 2. So we have a horizontal compression of a half. So it's a horizontal compression of a half. We have a vertical translation of negative, or shift down by -1. So we can write that. Now this c is equal to 0. Because c is equal to 1, not 0. I mean, there's no change of y value. No reflection either. So we can see here we have a vertical translation of 1 unit down. So we say translation 1 unit down. So we know this graph will be sliding down, okay? Then we have, there's no horizontal translation, so our asymptote will be the same as the original function. But we have a compression. So we have a compression, a horizontal compression, of a half. That's what we got here. So this is our equation. We have y is equal to log 2x minus 1. So our x coordinate here, if we were to translate it, okay, what do we have here? We'll have x would be x over a half, or x over 2 in this case. So maybe I'll rewrite this as 2 here, so it makes it much. So d is 2. So we have here x over 2. Now there's no horizontal translation. And we have cy plus k. So in this case, we have k. We have y, right, minus 1, because your k is minus 1. Just remember this is going to be x over d plus plus the value for the translation. There's no translation, which is h. It's going to be h. It's going to be cy minus or plus k. There's no change in the c. So now we have x over 2 for our x value, and your y, we can actually put it over here. So no, we don't need this because we need to find our x and y. So this will be eliminated. So we don't need this column here. Because we'll find a new set of x and y value. So then we have y minus 1. So we put a column here. This is my y. Because the y will shift. Basically by minus 1. We can put a minus 1 here or minus 1 all the way through. And we'll have the same value. But we'll go ahead and calculate it from the beginning here. So x over 2, so we have a quarter, right, divided by a half. So we don't need, we can remove this now because we don't need this 0. So if we do that, this is going to give us, so x is a quarter. So 1/2 divided by 2. So what do we get here? And that gives me 1.25 or 1.25. The y now will be -2, -1. Let's get up to that, which gives me -3. So that's my first coordinate points. And continue the trend. We have half divided by 2. And that will give me 0.25. And so -1, -1 gives me -2. That's my next coordinate point. Next, we have 1, 2, which is half. So that remains 0.5. Now we have 0 minus 1 will give us -1. So that's the next coordinate. We have now 2 over 2 will give us 1. And now we have 1 minus 1 to give us 0. Next, we have 4 divided by 2, 0x. So 4 divided by 2 gives me 2. Now I have 2 minus 1, 2. Oh, 2 minus 1 it could be 2, could be, has to be 1. Next, we have 9. Oh, let's be a 2, 1. Should I do, we have x9. No, we got 9 here. Oh, this should have been 8. Oops. So my graph is actually a little bit skewed here. Oh, I'm seeing my errors here. It's a mistake here. 2 to the power 3 is 8. So those give me, there's my graph. Now that's a corrected graph. Good thing I did it in pencil. Now this can be 8 divided by 2, which is 4. 3 minus 1 gives me 2. So let's go ahead and sketch our transform graph. Now we have x is to be -3 is down here, we put here. So we have 0.125, -3 is about here. So I'll do that in a different coloring. So maybe this might. Then we have 0.25, -2. So 0.25, which is about pretty close. Not the same. Then we have 0.5, -1. We have 1, 0. X is 1, y is 0. So right here. 2, 1. And 4, 2. So graph shifted slightly, but not a lot. So continue. Now, if we were to select another value, so this graph will continue. So we have a horizontal regression, so graph should continue. So from our translation here, so we have no y-intercept. So actually we're doing it here. So we have a vertical asymptote, y equals 0. Sorry, x equals 0 here. Oops. This is okay, x equals 0 is our so x equals 0 is our vertical asymptote. Our x-intercept is equal to 1, okay, 1, 0. The domain is where x is greater than 0. The range y set of real numbers. we can say there is no y-intercept. Oh, no y-intercept.